Well, we're going to go on with the next segment now. Up to this point, there hasn't been anything new in principle over and above what you've all known for a long time. The emphasis has been entirely on the approach, with emphasis also on the motivation for why these various techniques can be useful. But probably your feeling about most of it is, well, after all, it's all pretty obvious, and it's nice to be reminded of it. Now, for the first time, we're going to talk about a new principle that you won't have heard about before. And this is a principle which has a number of uses. It's most useful as an analytic technique, whose objective always is to simplify or save work, or both. The first application of this new concept is going to be the Extraelement theorem. But we're also going to use it for a couple of other things later on. So, because it's a new concept, I'm going to have to go a little more slowly, and you're going to have maybe a little trouble in believing why this is a very simple and yet useful thing until you practiced it a little bit. So to start off, I want to introduce the notation and the constraints on the system in terms of what you already know. What you normally do in dealing with analysis of a system is that you're solving for some transfer function. The gain is a typical transfer function, but not the only one. Input and output impedances are also transfer functions, and there are plenty of others as well. But what you normally do is you apply a single signal to the system, and you measure a corresponding dependent signal, which you call the output. And the ratio of the output to the input is the gain. But more generally, the ratio of any dependent signal to a single independent signal is a transfer function. And most of what we learn, especially at the beginning, about the analysis of systems is that this applies to linear systems. I talked a bit about that already. The same constraint is going to apply when I generalize this concept now to talk about null double injection, which is the new concept that we're going to discuss. What you see right here so far is defining some notation. We have on the left an independent driving signal, U sub I1. I'm using the symbol U because I don't want to call it a voltage or a current or anything. In fact, it could be a lot more general than that. If it's a mechanical system, the independent input may be a torque, for example, or a force. So U is an independent signal represented by a generator in circuit symbol notation. The sub I means input or independent, and the 1 simply means it's the first one that I'm talking about. Okay, now if the system is linear, and that's the only constraint that it's necessary to put on it, if you provide an excitation in the form of a single independent source, every other signal in the system is linearly dependent on that input. Linearly dependent means that every other signal is proportional to that input. I'll make some rather specific examples in order to make this idea concrete, even though what I'm setting up is completely general. Suppose the independent driving signal is a voltage or a current, and I walk around inside the system, inside the black box, carrying a voltmeter and an ammeter. I can stick those meters down in any branch or at any node in the system, and the reading I get on all of those meters is something which is proportional to the input signal, in the sense that if I double the amplitude of the independent driving signal, I double the reading of the meter wherever it is I place it. So the next thing I'm going to do, walking around in this box, is I'm going to settle on one particular point and call it output number 1. Really, it's only dependent signal number 1. And again, I don't care whether it's a voltage or a current or whatever it may be. It's a dependent signal that I've identified with a subscript 1. So it's a UO1. And the only thing that I can say about it is it's proportional to the independent input, and the proportionality factor is something I'm going to call A1. A1 is a constant if the system is linear. Constant in the sense that it does not depend on the signal amplitude, although of course it may be a function of frequency. All right, I've now set down one of the 2 meters I'm carrying around. I can walk somewhere else inside the system and settle on another place and connect the other meter in there. And it also gives me a reading which is directly proportional to the single independent input, and in general the proportionality factor is different. So that's B1. All of that is what you're familiar with already. That's what you do all the time. And when you do analysis of that system, you draw a model of the system in order to find the values of those coefficients A1 or B1. Right. Now, the next thing I'm going to do is the system is still the same, but I've taken away the first input. And I walk around somewhere else and I apply a different independent input signal at a different place. But the 2 meters are still where I left them the first time. But they're now going to give readings which are directly proportional to the second independent input. And because that's in a different place, in general, I'm going to get different proportionality factors, even though the outputs are in the same position. And that's pretty obvious, too. So all I've done so far is establish 4 proportionality coefficients. Now I'm going to do the first thing, which is a little bit different. I'm going to apply both of those inputs at the same time. Meters are still in the same place. And I can predict what the meters are going to read. Because the system is linear, again, each meter will read the linear superposition of the 2 values that it would have if I had each of the inputs separately. Linear sum, that's all. Again, bear in mind that if these coefficients are frequency dependent, they are complex quantities or they have magnitude and phase. And when I say a linear sum, I mean a phasor sum, taking into account the phase angle. Now, this doesn't seem very interesting yet, because what it means is that according to the relative values of the 2 inputs that I'm applying, the readings of those meters can wander around and take any old values. So that doesn't appear to be useful. We're going to see in a moment why it's useful, but let's pause momentarily simply to review the definitions of these 4 coefficients by working backwards from the general case where I have both inputs together. In other words, the definition of A1 is it's output number 1 divided by input number 1 if input number 2 is 0. So this is simply a notation illustrating what the definition of the A1 is. And the same for the others. A2 is output number 1 related to input number 2 if input number 1 is 0. And the same thing for the other 2. Now, go back to the general case, and let's see why this is a useful thing to do. I can make either of the outputs have any value I like depending on the relative values of the 2 inputs. Is there an output I would like better than any other? Remember, the objective of analysis methods is to make things as simple as possible and get the maximum information out of it. What is the simplest value a quantity can have? 0. So let's make output number 1 0 and see whether this is of any value. a priori it may not be, but let's try it and see, simply because 0 is a simple quantity. So, suppose I adjust the two inputs relative to each other until output number 1 is 0. I can detect this because the meter connected to output number 1 will go to a null, or down to the noise level. The point about this relationship is there is always a possible combination of the two inputs that will make that happen. The trivial solution is, of course, both inputs are 0. That's obviously not interesting. But there's one other non-trivial solution where both inputs are non-zero, but you can adjust them until the output is 0. Notice that what you do in that case is that you fix the relative values of those two inputs. Because if you solve that equation, you end up with a ratio of the two inputs, which is a unique value. It's equal to the negative of the ratio of the coefficients, which is a fixed value. That is the ratio of inputs that you have to apply in order to null that output. Now, while you're doing this, looking at meter number 1, making it go to 0, meter number 2 is also wandering around, of course, while you're making the adjustment. But as soon as you stop adjusting, settled on the condition that makes output number 1 go to 0, meter number 2 now stops wandering around. And it stops at a reading which in general is non-zero. And this equation tells you what its value is in terms of the parameters. We have now fixed the relative values of the two inputs, because it's the same two inputs that appear in the second equation. Now I can eliminate input number 1 between these two equations by simultaneous solution. And it's obvious that in about one line, this is the answer you get. Output number 2 divided by input number 2 is equal to this combination of the four coefficients. And the first partial result is to notice that this is a different answer from the ratio of output number 2 to input number 2 that we already had previously, which is the coefficient B2. In other words, the ratio of output 2 to input 2, which is the ratio of two quantities, has two different values because the conditions are different. In the original condition, in the previous picture, the other input was 0. And the answer for the ratio of output 2 to input 2 is B2. In the newest result, the ratio of output number 2 to input number 2 is different because input number 1 is not 0. But input number 1 has a specific value, namely the value that nulls output number 1. So that's the importance of these constraints that are placed on the ratio. That's what makes the two answers different. So I say this is the first partial result, so let's stop for a moment here to make sure you believe that. Because this is not the normal result. Normally, for a given fixed linear system, you expect to get a unique answer for any particular transfer function. This is probably the first time where you find that you can get a different answer for the same transfer function. Because what you normally deal with is the case where this is the only input, which corresponds to the B2 result. But now we have a new case. There's a hidden input that is not in the equation. It's hidden, but it's not 0. However, it has a specific value that has been used to establish an equivalent condition, namely that output number 1 is 0. But it's a different condition, and therefore you get a different answer. So that's the first important point. You can get two different answers for the same function because you're evaluating it under two different conditions. Well, let's sort of cogitate about that for a moment while we think experimentally of how this works. Because you can set all this up on the bench. And in fact, when I talk about this in the class at Caltech, I actually have hardware demonstration, which is one of several I use during the course. I wheel in a bench with equipment on it and scope and meters, and we have closed circuit TV so the class can look at waveforms and meters. And so I have a setup in which we actually observe this happening. And it's easy to visualize in terms of real sources. You have these two knobs on two separate generators and 2 meters to look at, or 2 traces on the scope. And I can make one of those knobs 0 and have a single input, and the meters move proportionately as normal. And then I can turn up the other input in the presence of the first one, and I can make one of the meters go to null, and the other meter stops. And it stops at a different value than it had when I had the second input 0. So when you think of it in real hardware terms, you can see that this is possible. There's a little complication to this, of course. If I'm doing this with AC signals, then of course I have to have frequency synchronization between the two sources. And what that amounts to is that they really come from one signal generator, and it goes into a T connector, and one end of the T goes directly into one of the inputs, and the other output of the T goes into a box that has 2 knobs on it labeled magnitude and phase. And that allows me to adjust the magnitude and phase of the second input relative to the first one, while keeping frequency synchronism. So when I'm adjusting to get a null, I have to adjust both of those knobs. Because if I only adjust one of them, then I can make the reading on the meter go to a minimum, but not 0. It goes to a minimum, comes back up. So what I do is I go to a minimum, and then I twiddle the other knob, the phase knob, and the minimum gets smaller, still not 0. And then I go back to the magnitude knob, so it's a kind of zeroing in. But it converges very rapidly with only about 2 adjustments. But in general, you do need the phase knob. Just to make it even more concrete, the meter that I'm using to do this is a narrow band voltmeter, which is actually part of a wave analyzer. And it has a 90 dB scale on it. So it's a very wide dynamic range, which is very good for demonstration purposes, because you can see everything happening in one range. And so we start out with readings that are on the order of 0 dB or minus 10 dB. And when I get a null, I can make it go down to minus 90. So it's a very sharp null because of the narrow band. So all of this is physically matchable in real hardware. Incidentally, the box with the magnitude and phase knobs is designed to have independent control of magnitude and phase. When you think about it for a moment, that's not quite such a trivial job. It's easy to adjust magnitude independent of phase. Potentiometer does that. It's not quite so easy to adjust phase independently of magnitude. So there's various ways to do this. And the first way I did it, I had an undergraduate student make a little project of building this box, which he did successfully. His name was Bill Hedges, so I always referred to it after that as the Hedges box. And then a few years later, we had a new graduate student who came from Taiwan, and as is common with Chinese students, they don't have much practical experience because they don't have much lab equipment in their own universities. What was different about this guy is that he knew that, and so he asked for a summer project just to learn which end of the soldering iron is hot. And so I had him build another one of these boxes using a somewhat different principle. And his name was Shiping Shu, so his box is the shoe box from now on. And that's the one I still use, although I had to have our staff engineer rebuild it to get rid of all the dry joints. But that's anyway, such a box can be made, and so that's what I use for demonstrations. Well, back to the question now of, okay, so this is possible. The next question is, what good is it? So what I'm going to do now is repeat this very simple derivation twice more, each time making it just a little bit more specific. So the next time through it, input number 1 and output number 1 remain completely general, but I'm going to say that input number 2 is a current. So I identify a pair of terminals, and input number 2 is the current that is stuffed into one of those terminals and, of course, yanked out of the other one. In fact, I'll do it right now. I'll write that current on there as well. It's the same current. The point about this is, it doesn't matter where that current comes from. And I've drawn it as a Norton equivalent, which is possible because I can represent any linear system at two terminals by a Norton equivalent. That's what Norton said. So it doesn't matter where the current comes from. Or another way of saying that is that the stuff inside the black box that I'm dealing with doesn't even know where it comes from. All it knows is that there is a current going in at that node. Okay, that's identified input number 2 as a current. At the same time, I'm going to identify output number 2 as a voltage across another pair of terminals. So I can go through exactly the same algebra again, which is identical. The only difference is that UI2 now becomes I, and UO2 becomes V. So the two results that I already derived are now V over I, output 2 divided by input 2. And again, I get two different answers for the same quantity because they are calculated under two different conditions.
So they're not exactly the same quantity.
They're the same transfer function. The question was that they're not the same quantity. Well, in one sense they are. It's the ratio of the same two quantities, the same transfer function. What is different is you get two different answers.
Because the physical conditions are different.
Well, because the other input is different. In one case there isn't any other input. In the second case there is another input, and it has a specific value, namely the one that nulls the other output. That's the hidden input. The reason you get two different answers is that the V has two contributions, one from each input. That's why you get two different answers. Maybe that's an easier way to look at it, in fact. If the other input is 0, you get a unique answer. If the other input is not 0, you can get any other answer, and this is a specific answer when the other input is not 0 and has a specific value, namely the one that nulls the first output. Okay, that's the second time through. Here's the third time through. All we're going to do now is say that output number 2 voltage is measured across the same terminals that input number 2 is driven into. So I just merged those two pairs of terminals. The algebra is still the same. And I get two different answers for V over I, depending on what the other input is doing. Same two answers in terms of the A and B coefficients. The only difference is the interpretation of this ratio, this transfer function. because it is now a self-impedance, because it's the ratio of a voltage to a current at the same place. It's what the circuit theory people call a driving point impedance. A driving point impedance is simply the impedance looking into a linear system when you apply a drive at that point. And so the notation is ZDP, driving point impedance, but you still get two different values for it, depending on what the hidden input is doing. Now, the only other modification in this picture is this is a lot of subscripts to keep writing down all the time. So I simply dropped all of them and except one, and called the first answer ZD and the second answer ZN. And you'll see the reason for that choice a little later. But for the moment, it's simply a matter of making it a simpler symbol. So translating the result now to the special case, you get two different answers for the driving point impedance at a specific pair of terminals, depending on what the hidden input is doing. Okay, that's the second intermediate result. Now, we still don't know what's the purpose of all of this. That's the last step, which we now do very quickly. Same linear system, but there's no input number 2 and no output number 2. Only input 1, output 1. So the only parameter that we have is the coefficient A1, which is output number 1 divided by input number 1 when input number 2 is 0, because it isn't there. We can analyze the system to find A1 because this is what we normally do when we calculate gain or whatever. But suppose after we've done that, we decide later on that somewhere else in the system, namely this pair of terminals, we want to add an extra impedance, Z. So I put that impedance there, Z. Now suddenly there exists a voltage and current at those two terminals. There's only one input now, input number 1. But there is an implicit input number 2, namely the value of this current I. Now remember, the stuff inside the black box is fixed and constant, and it doesn't know where the current I comes from. But we've already analyzed that part of the system. But now, in the presence of this impedance Z, we are now enforcing an external relationship between V and I, namely Ohm's law for the impedance. And because of the choice of polarities, I is minus V over Z. But the two sets of linear equations that belong to that black box are just the same as they were before. Namely, the A1, B1, A2, B2 are still the same as they were before, because they're properties of the box independent of what's connected outside it. So the same algebra applies. Output number 1 is the linear superposition of A1 times the first input plus A2 times the second input. But the second input is minus V over Z. Because remember, the box doesn't know where the I came from. It thinks it's an external input. So you make a direct substitution in the equation. And the second equation says output number 2 is B1 times input 1 plus B2 times input 2, which again is minus V over Z. And now you see you have V in 3 places. So you solve the second equation for V, substitute it into the first equation, and all you have left is output 1 and input 1. And when you solve it, you get this line. And you see we have a couple of combinations of the original coefficients, which you recognize as these 2 driving impedances that we already solved for. On the top we have the Zn, and on the bottom we have Zd. So if I make that substitution, you get this line, and you see what this says is output number 1 divided by input number 1 in the presence of the element Z is equal to A1, which is the same ratio of output number 1 to input number 1 before the Z was applied, multiplied by a correction factor. And that is the extra element theorem. In other words, we've derived what the objective was. If you've already calculated the gain of the system, and you decide later on you want to put a certain element Z in addition, all you have to do is multiply the answer you already got by a correction factor that involves the extra element itself, the Z, and 2 parameters, Zd and Zn, which are the driving point impedances of the original box at the place where you are going to add the extra element. And that's the theorem. And I talked about the motivation for that at the beginning. And this is the derivation of it, and you see it's pretty simple. And I emphasize again, the Zd and the Zn are calculated on the original box. And I very carefully, during the derivation, did that before I even mentioned the Z. In fact, the Z was the last thing that appeared. So all of the parameters in the formula, the original gain and the 2 driving point impedances, are properties of the original box. And you never calculate anything on the box in the presence of the Z. All you do is substitute into this result, and that gives you the answer, in place of solving the whole system. So that is the extra element theorem. And you see, the only catch to it isn't really a catch. The only thing that causes a little difficulty is one of the driving point impedances, namely Zn, is calculated under this null double injection condition, in which you have 2 inputs simultaneously and you adjust them in order to null a different quantity. That's the new idea that you haven't thought about before, and that is the essential step in calculating the Zn. That's the only new thing you have to know, and therefore practice. Once you know how to calculate Zn, you can use the theorem. And that's all that it amounts to. To use the theorem, which is the value of it, you don't have to remember the derivation. You don't even have to have understood it. But that's the same with most theorems, of course. But you do have to know how to apply the null double injection condition, because that's the essential feature of calculating one of the parameters. Now, I'm pretty confident in saying you haven't seen this before, unless anyone wants to refute that, because I've never found it in any book or in any literature. And even though I developed this a long time ago and I've been teaching it Caltech classes. And more recently, I've also been including it in all of these outside courses. And I keep asking the question, has anyone ever seen this before? And no one ever had. But I never published anything on it, because I simply couldn't believe that this hadn't been done before. After all, there isn't much new left to do in linear system analysis. It's been around a long time. It's pretty hard to find anything this simple that hasn't been done before. So I was always reluctant to publish, because I knew the moment it came out, I'd get letters from all over the world saying, "Oh, you dummy, so-and-so did this in 1923. But finally, after talking about it more widely and still never hearing about it from anywhere else, I finally took the plunge. And so I wrote a paper on it, called it the Extraelement theorem, null double injection or something. But I still chickened out, because I didn't submit it to the IEEE transactions on circuit theory. I submitted it to the IEEE transactions on education. That's a cop-out, because you can pretend then that if someone says it's done before, well, you knew that already, but you can do that in education proceedings because it's a matter of the approach, and you don't have to claim that it's new. So anyway, it came out in the education transactions 2 years ago. Never heard a word from anyone. That says one of two things. Anyway, during the time before I did that, and I was searching for other places where it might be, the closest I came to it was in a place where the objective was different. Because when you look at this result, what it is saying is any transfer function of a linear system is a bilinear function of any specific element in it. Any specific element is z. Now, I could multiply top and bottom by z and write the z plus zn over z plus zd, and that would be the same thing. That's a bilinear function, in the sense that it's a ratio of two linear functions of z. Because we know that z is not inside any of the other quantities. We're clear on that now. So any transfer function of a linear system can be written as a bilinear function of any particular element in it. And the place where I found that talked about was in Boddy's famous book, Network Analysis and Feedback Amplifier Design. And he derived it in order to prove this second statement. In fact, there it is. You probably can't see that either. Maybe it's recognizable enough. If you look at this expression here, the zt is the same as a transfer function, and the little z is the same as my big one. That's the specific element. And you see it is indeed a bilinear function. And that was Boddy's objective, was to show that it was a bilinear function. Then it was a very simple derivation. In fact, it occurs on page 10 out of a book that's over 400 pages. So that's a pretty basic result. But you see, what he didn't do is he didn't notice that if he divided through by these two deltas in the first position and identified the resulting coefficient as driving point impedances, he would have had the extra element theorem. But he didn't do that. So he came that close, but he was proving something else. But now, it's fine to say that any transfer function of a linear system is a bilinear function of any element in it, but what's the use of knowing that? As far as I can tell, the only use for it is, in a sense, a negative kind of application, in order to say that it is never more than a linear function. That is, it can never be a quadratic function or a cubic or any higher power. And the only value I can see of knowing that is that if you analyze a linear system and you come up with a gain or whatever, and it has R23 squared in the answer, you made a mistake. That can't happen. So, in that sense, you can use it as a sort of partial check that you didn't make that kind of mistake anyway. And that doesn't mean that you can't have R23 squared somewhere along the way. I'm sure you've encountered that. In fact, we already did that right here. The very first circuit we analyzed when we were talking about low entropy expressions. We calculated the ratio of two determinants, just like Bode was doing. And here's an intermediate result, and it has RB squared in it. But it cancels out before you get to the final answer. So what that theorem is saying is, it had better cancel out. And if it doesn't, you made a mistake. Okay, back from that little diversion, let's go back to how useful the theorem is, which is the only value. So the implementation of the theorem is, you want to add an extra element and correct the answer you got already. The only new work you have to do is calculate these two driving point impedances at the place where you're going to add the element, and you don't even have to know yet what the element is. All you have to know about it is where you're going to put it. Okay, how do you feel about that? Do you feel it's worth going ahead and seeing how easy it is to use now? Because that's all we're going to do from now on, is practice doing examples to see how easy it is. But you see, we have to do that. Because if we don't, and I just leave you with the theorem, you say, fine, very good, and you go back and never use it. So we got to see how easy it is to apply it. Okay, here's the first example. And we'll use the basic common emitter amplifier that we already used. I mentioned at the beginning, this is going to be the vehicle for a lot of things to practice these shortcut techniques. That has two advantages. Not only do we practice the newer technique each time, but we get to re-practice the earlier ones to get back to the same point again. And in this particular case, here's the small signal AC model of the basic common emitter amplifier with the bias stabilizing resistor R and no coupling capacitor and no bypass capacitor. So we do the straightforward analysis, getting a low entropy result. We spent quite a bit of time already showing various ways to arrive at the low entropy result by minimizing the amount of work, taking advantage of doing the algebra on the circuit diagram, using Thevenin's and Norton's theorems to remove loops and nodes. Now, let's do it all in our heads. So, let's take the approach of removing the first loop by Thevenin reduction. So that gets rid of the RS and RB divider directly as a multiplier on the Thevenin equivalent source voltage, so that divider will show up as a multiplier in front of the gain. Then we'll have a single loop here with RS in parallel with RB. We then reflect that into the emitter, at the same time dividing it by the ratio of the emitter to the base current, which is 1 plus beta. This leaves the Thevenin equivalent voltage across RE in series with R, in series with the reflected base resistance. Therefore, determining the denominator of this expression, which gives you the emitter current as a function of the Thevenin voltage. Multiply the emitter current by alpha to give you the collector current, multiply the collector current by RL to give you the output voltage, and that's the end. So you've built a low entropy expression by writing the answer in one line. Substitute numbers, compute the answer, comes out to be 2, converts to 6 dB. Now let's imagine that we've done all that horrendous amount of work, and we decide later on that we want to add something to the model. In particular, let's add the bypass capacitor around this bias stabilizing resistor. And even though in this example, obviously, it wouldn't be that much work to go back and do it again, let's use a simple example to illustrate the extra element theorem. So, the approach is, we're going to add an element across R. And without knowing what it is yet, all we have to do is calculate the two driving point impedances seen across those terminals. So the first thing we have to do is calculate ZD, one of the two. Okay, ZD is the driving point impedance found by applying a second external input with the first input 0. UI1 is V1, so V1 is 0. So this is single injection. Nothing new conceptually about this at all. You're simply going to calculate the impedance, driving point impedance, that exists across that resistance. Once again, it doesn't matter where that source comes from, which is why I chose a Thevenin equivalent this time, just to make it different. It doesn't matter. I don't even have to draw a source at all. But I'm drawing it anyway for the time being to emphasize the fact that there is an external source. It's what we called input number 2. Okay, all you have to do is solve for the ZD impedance looking in between those two terminals. And in this simple example, the answer is obvious by inspection. You're going to see the resistor R right across there, but there is a parallel path. So again, in our heads, we can do the circuit reduction. V1 is 0, RS and RB are in parallel, reflect them into the emitter divided by 1 plus beta. So the parallel path consists of RE plus the reflected base resistance. And that's all, because when you get to the base, having reflected those resistors, the base then becomes AC ground. So this pair of resistors in series is in parallel with R. So that's the answer for ZD, which is, of course, a resistance RD in this example. Numerically, RE is 36 ohms, RB is 10 parallel 8.6, and when you reflect it, it's divided by 1 plus beta. The result is 39 ohms. 39 plus 36 is 75. 75 in parallel with 2.2K is still 75 ohms. So what that tells you is that the dominant component of the driving point impedance ZD is the path through RE. The path through R is almost negligible. In other words, most of the current that is being driven in from the second source, most of it's going into RE, hardly any of it's going into R. Okay, well, conceptually, there was nothing new about that. Now the other one, calculation of Zn. This is the conceptually new one because we have to calculate this under the conditions of null double injection, which means that we have not only the second driving source, which we're applying externally in order to make the measurement, but the other input is now restored. So we have double injection. But we have to adjust those two sources to achieve a specific condition. Namely, output number 1 is nulled. Output number 1 is V2. So you visualize twiddling the knobs, actually using one directly from the generator and the other one going through the shoebox with magnitude and phase knobs. And you twiddle the magnitude and phase knobs of the second input relative to the first one until the meter hung on V2 goes to 0. Then you don't twiddle anymore. Then you take a pair of meters and you measure the voltage across the second source and you measure the current that goes in. And that ratio, by definition, is Zn, the driving point impedance seen by the second source in the presence of the hidden first source, which is adjusted to null the other output. So that's the hardware implementation. Analytically, all you have to do is calculate this impedance looking in under the condition of nulled output. This is the only new thing conceptually you have to do. So I describe now what the sequence of argument is that enables you to do that. The way you do it is you start with the null and you propagate the consequence of the null towards the second source. The purpose in doing that is you want to know what happens to the current going in from the second source. That's what enables you to calculate the Zn. So you start with the null, which is an established condition, and you make the following argument. If V2 is 0, there must be 0 current in RL. So there must be 0 collector current. So there must be 0 emitter current. So all of the current from the second source goes down R, therefore Zn equals R. Easy, isn't it? It's a logical sequence of argument to say what is the consequence of having adjusted the null. And the consequence is all of the current from the second source must go down the R because the null propagates. This is why setting something to 0 is so useful. Because if one thing is 0, a lot of other things are 0 too. And notice that one other relationship that we've adopted along the way builds on the fact that we already talked about, the fact that the ratio of all of the three currents of the transistor remains constant, which means that if one of the currents is 0, all of them are 0. And that's what's happened here. The collector current is 0, therefore the emitter current is 0. And that's all you need to know to arrive at the answer for Zn, which is the objective of this calculation. So Zn is equal to R, 2.2K. Now, because that's a new concept, you have to think about it a little bit. By this time, I think you probably understand what null double injection means. But that isn't enough. You have to believe it. Believing is more than understanding. And the belief only comes with a little familiarity resulting from practice. but I think you can see the process is simply a logical succession. It's unique. One thing follows another. There's no ambiguities. There's nothing to guess. So it's a unique, straightforward process. And the only thing that's difficult about it is that you haven't done it before. It's a new idea. And because it's a new idea, I want to go through the same steps again in a pictorial manner. Instead of following the logical sequence of argument, I'm going to show some overlays There's the same circuit, same topology with a little different scale. I'm going to start at the beginning of the calculation, which is finding the voltage gain V1 to V2 in the normal single injection conditions. Barely getting it in. Okay. Here's an overlay which is intended to suggest, in a very qualitative sort of way, the strength of the current that exists in the various branches. The width of the trace represents how big the current is. So what happens is V1 drives a current into RS, which splits. It's a current divider. Some of it gets lost in RB, some of it goes into the base, where it gets multiplied by beta in coming out the collector. And the emitter current is the sum of the base and collector currents. 1 plus beta times IB. In this qualitative sketch, of course, the value of beta is about 2. Okay, and the result of this calculation is the gain A0, V2 over V1, which we did to begin with, and it came out to be 6 dB. Okay, that's the reference gain, the gain of the circuit before we've made any changes. So now what we're going to do is calculate the two driving point impedances at the place where we're going to add the extra element. So this is how we calculate ZD. We apply a second source across the terminals where the extra element is going to go, and we make the other source 0. So it's single injection at a different place. And this is what happens to the current. The current that you stuff in, now I've drawn an ideal current source. I keep changing it every time, just to emphasize it doesn't matter. Whatever current goes in splits. A little bit of it goes down R, most of it goes into RE, a little bit of it comes out the base, most of it comes out the collector. Alpha times the emitter current comes out the collector. What comes out the base gets divided. Some of it goes down RB, some of it goes down RS. So that gives the result for ZD. R in parallel with RE plus the reflected base resistance. Now we get to the hard part, both analytically and pictorially. Null double injection. Can you see everything there? So I'm got a hard time placing this now. Okay, this is one of the independent inputs giving you the yellow current. Now I'm going to superimpose the other one with the blue current that comes from the other input. Well, that's about as close as I can get it. Now, where it turns green is null. I hope it's green. And you see what has happened is that if you look at these two arrows, the blue arrow is down, the yellow arrow is up, and they're equal in magnitude. This is how you get the null. You've made those two currents equal and opposite by appropriate adjustment of those two sources. So they cancel out. That's how the null develops. And you see the propagation of the null now becomes obvious. Because the only way you can get a null at the output of the transistor is to have a null at the input as well. Namely, both the base and the emitter. Therefore, all of the current from the yellow source must be going down the resistance R. Here the blue and the yellow are in the same direction, so they add, you see, they don't cancel. And the total width is the same as the width of the yellow current that was going in, because the green is 0. Okay, now the only non-zero currents are those. Now if I take the first two away and leave only the net result, subtracting out the null part, that's all that's left. And this makes it even more clear now why the answer for Zn is just R, because the null that you get at the output implies zero drive to the transistor as well, which you have set up by adjusting the two sources so that the drop across RB caused by this loop current is matched exactly by the drop across R caused by the other loop current. You've made those two equal, leaving zero voltage across the base emitter of the transistor, therefore zero drive, therefore zero output, which is the null. So that's another way to interpret the condition of null double injection. Does that help any in understanding what null double injection is and how you calculate Zn? Well, I hope so, because it took me about 4 hours to make those view graphs. Okay, well, that was a little diversion in the sense that I went through the derivation again using the pictorial approach, so let's go back to the first one. It seems to be taking a long time to do this, but that's only because it's the first time through. And we haven't even mentioned the extra element yet, but that's the very last thing that's necessary to do, because we've now found the two necessary driving point impedances, which are across this resistor R. So the last thing is we put the extra element in there. So the extra element is a capacitor. And all that's left to do is to substitute into the theorem. The gain of the stage in the presence of the C2 is the gain that we had to begin with, which is the original reference gain modified by the correction factor that involves the element that we're putting in, which is Z, and Z is 1 over SC2, and the two driving point impedances. In this case, RD and RN. And you see the correction factor immediately gives you a pole and a zero. So that defines the zero at omega 1, the pole at omega 2, and there's the definitions. And you have a choice of whether you use the zero frequency gain as reference and the normal pole and zero, or you can invert the pole and the zero and use the high frequency gain as reference. It's interesting to notice that the corner frequencies involve the capacitor that you've added, and the resistance that goes with them is RD for the pole and RN for the zero. And from the definitions we have here, you can verify that the gain bandwidth trade-off works, because AM can be found from A0 times the ratio of the corner frequencies, and when you make that substitution, it comes out to this result, which, as you would expect, is the same as the A0, except that the R has vanished, which is what happens, of course, at the high frequency limit when the C2 bypasses the R out of the picture. So that's the end of the first example of how easy it is to apply the theorem. There's a few things along the way that it's worth pointing out. Nulling a voltage is not the same as shorting it. If you short it, then for sure you've nulled it. It's going to be zero. But it's not zero because you cancelled out two opposing currents. Notice that after you've nulled it, then you can short it. But you don't achieve the null by shorting it. Another thing that you can note is even from this very first example, the null double injection calculation was actually easier than the single injection one. The answer was only R instead of a more complicated combination. Now that's not an accident. The null double injection calculation is always easier than the single injection one, for the same reason I mentioned before. If one thing is nulled, a lot of other things are nulled. The answer is necessarily simpler. Now, you may not believe that right now, but the reason that it may seem the other way around, that the null double injection calculation is harder, is simply because of unfamiliarity. Here's the final result for that particular example. The reference gain was A0. A0 is 72 hertz. The pole was 2.1 kilohertz, leading to the final flat gain of 36 dB. In a typical application, of course, the mid-band gain is probably the one which is most relevant to the specification. And the bypass capacitor there is simply to eliminate the effect of the R as far as the main gain and frequency response is concerned. So the high value of gain that you get is the one that you have to meet the specification with. You also have to meet the specification for this corner frequency, because you have to maintain this gain down to some specified value, and there probably isn't even a spec at all on the other one. So an important result from all this is it's the value of the F2 which is important for the specification, and the F2 is the pole, and the pole is determined by the RD, and the RD is the small one, 75 ohms, because it's dominated by the parallel path and not the R. The 0 is determined by the R, but that's not the one that's usually important for the spec. It's the pole. And so it's a common error to guess that the bottom end of the frequency response is determined by the C2R time constant. It isn't. It's the wrong corner. I'm sure you know all that because you're experienced with these things, but a lot of people, students especially, they don't realize that for maybe quite some time. So the extension to your backlog of knowledge is that you can get both the pole and the zero directly in terms of these two driving point resistances. Well, it seems to have taken a long time to get through that, but as you'll see shortly, we're going to do several examples of this, and it'll get to be a lot easier each time. And there are a number of extensions to talk about also. But first we'll take another break, 10 minutes or so. Okay, we've completed the first example, and I've reviewed some of the generalities that can be developed from that, which is basically the null double injection calculation is actually an easier one to do than the single injection calculation, and it's simply a matter of getting familiar enough with it that you believe that. There's a couple of other subsidiary points that you might think about while all this is marinating in your mind, which is going to have to do for a little bit. In fact, let me repeat the derivation of the Zn yet a third time. Back to the first method again. Remember, the way you calculate Zn is you have both sources present, both the original input and the second source, for test purposes. You adjust the two of them in magnitude and phase until the first output nulls. You propagate the null back to the second source, because the objective is to find what happens to the current from the second source. Where does it go? And the argument is, if V2 is zero, zero current in RL, zero collector current, zero emitter current, and that tells you the answer you need. All of the current from the second source goes down R, so the answer is R. Now, another important aspect of this is the things that you don't need to know to get this answer. And the most obvious one you don't need to know is V1. It certainly affects the answer. That's what determines the answer. But notice that the calculation of Zn did not involve V1. But it did involve an equivalent piece of information. The equivalent piece of information is the null. That's what was used. Then we propagated the null, which is using the fact that the null exists. That's what took the place of the knowledge of V1, because there's a unique relationship between V1 and the second source that produces the null. So if you know a null exists, this is the same thing as knowing what V1 is. You don't need both. It's the same information. So, in fact, all that you've used to calculate Zn is the fact that the null exists, and you don't need to know the V1 that caused it. That's why the argument simply followed the null back to the second source, and you never had to know what went out here. Now, if you want to know what goes on out there, you can find out. For example, the IB is zero as well. And that's what gives rise to the other interpretation in terms of the pictorial representation. Here's the two overlays again. Where it's green is null. And you notice the base current is zero also. Necessarily, because if one current in the transistor is zero, all three must be zero. But you didn't need to know that to find the answer, but you can follow it through and determine it if you want, even to the final stage, which is eliminating the null from the picture and showing only the remaining two loop currents. In other words, we set up the condition that the voltage drops across RB and R are equal. And this illustrates perhaps even more clearly why it's only the null that you need. Because implicitly, to get a null, the voltage across RB must have the same value as the voltage across R, because that's how you get the null. And the value of V1 necessary to get it is the value of V1 necessary to give that voltage across RB. But you don't need to know that, simply for the purpose of calculating the Zn. So that's another little viewpoint to do with the calculation of the null double injection condition. You're using an equivalent piece of information to the other input, which is why you don't need to know the other input specifically. Okay, now let's go on with the next extension of the extra element theorem. I've introduced the theorem for adding an extra element in parallel across a node pair. That is, the reference value of the extra element is infinite. It's not there. You can easily visualize a case where you might want to add an extra element in series with a branch. That is, you want to break a connection. You want to cut a piece of wire and insert an element in series with the branch. That's obviously the dual case. So you would expect that there is a dual form of the theorem also. Sort of like Norton's and Thevenin's theorems are duals of each other. And the same is true for a lot of circuit theorems. And it is also true for the extra element theorem. But you don't have to rederive it from scratch. A simple algebraic relationship tells you how to find it. Here's the version we've set up already. The gain of the system in the presence of an element z is equal to the gain when z is infinite multiplied by the correction factor. Notice that if you let z go to infinity in the correction factor goes to 1, and of course the gain goes to the gain when z is infinite. That's essentially the definition of the coefficient. We can do a little algebraic manipulation and bring out Zn over Z from the numerator, Zd over Z from the denominator, which has the effect of inverting the ratios in the correction factor. The Z out front cancels, and you're left with Zn over Zd times the gain when Z is infinite. And all you have to do now is understand what the significance of that entire factor in front is. And what it is must be the gain of the system when Z is 0. Because what's left goes to 1 if Z goes to 0. Let me say that again. Take the correction factor in this expression and let Z go to 0. What happens? The factor goes to 1. So what's left must be interpretable as the gain of the system when Z is 0. So finally you can write it in this form that I've written under the other one, and that is the dual form of the theorem. It's a different choice of reference. In the original version of the theorem, you get the gain in the presence of Z in terms of the reference gain when Z is infinite. In the other form of the theorem, you get the gain in the presence of Z when the reference value of the element is 0. So you have your choice. If you want to add an element in parallel, you use the first version. If you want to add an element in series, you use the second version. And the correction factor is almost the same. The only difference is that these ratios are upside down. Same Zn and Zd. Notice the analogy with this entire calculation with the frequency response of the gain in terms of 0 frequency reference and infinite frequency reference. The same thing. The only difference is the variable now is impedance instead of frequency. And instead of corner frequencies, you have driving point impedances. But the algebra is the same. So you can express the gain of the system in terms of the gain when frequency is 0 and a normal pole in 0, or you can express the gain of the system in terms of the infinite frequency gain and an inverted pole in 0. So the algebra is identical. The variable is now z instead of frequency. That's all. So this relationship is not surprising. So let's do an example of that one. And again, to keep as much the same as possible, let's take the same circuit. Except this time, we'll start out with the common emitter amplifier stage with the emitter stabilizing resistor completely bypassed out. So this is the mid-band model now. And once again, you could go through the mental circuit reduction, eliminate one loop by Thevenin, which gives you the Thevenin divider in front, reflect the base resistance into the emitter. Thevenin voltage is applied right across the combination. So the denominator gives you the emitter current multiplied by alpha multiplied by RL. The result is 62 or 36 dB. That's the mid-band or infinite frequency gain when coupling and bypass capacitor are zero impedance. So suppose we've done that. And now we decide we want to find out what happens at lower frequencies when the bypass capacitor is no longer a complete short. So we want to put a non-zero impedance in series with the RE. So to use the Extraelement theorem, the first thing you do is break the circuit at the place where you're going to put the extra element, and you calculate two driving point impedances. First, ZD. So this is a single injection calculation. You make the original input 0, apply the second input by itself, ask what is the impedance looking into the circuit from that point. And the answer is, by inspection again, because it's easy enough, RE plus the reflected base resistance. I've called it an RD prime this time because it's a different calculation than the previous one. So that's easy enough. The null double injection calculation. Apply a second driving source and restore the original source. So it's double injection. Imagine that you've adjusted the two sources in magnitude and phase until you null the first output. Propagate the null back to the second source and see what happens to the current. So the argument is exactly the same as before. If V2 is 0, you have 0 current in RL, you have 0 collector current, and you have 0 emitter current. And this time, the emitter current is the only current that goes through the second source. So the conclusion is that regardless of the voltage applied by the second source, 0 current is drawn from it, therefore the driving point impedance is infinite. Again, you don't have to know what the V1 is. You don't have to know what happens in the left-hand part of the circuit in order to get the answer that you're looking for. So those are all the calculations you have to do, and the only thing left is to substitute these results into the theorem. So finally, you put the extra element in. And now you see another very simple extension of the theorem. The extra element need not be only one element. It can be any two-terminal combination. Simply a matter of what you substitute for the Z. So in this case, the extra impedance is actually a parallel combination of the R and the C2. But you don't have to know that until the last step, because you've already calculated the RD prime and the RN prime. So now the reference gain using the series form of the theorem, The reference gain is AM this time, corresponding to infinite frequency, and the correction factor reduces to the denominator part only because the Rn prime is infinite. So the numerator is 1, and in the denominator you have a little more complicated combination for the Z now. Now it's the parallel combination R together with a single pole caused by the time constant of the R and the C2. So this time you've got one more line of algebra to do to get the final answer into standard factored pole zero form, which you do by cross multiplying. That brings the 1 plus SC2R up into the numerator, and then you have to combine some terms in the denominator, namely R in parallel with RD prime, and you recognize that as the original RD we had in the first example. So you end up with the same answers we had before, which of course you have to do because you're ending up with the same circuit. We just started at the other end of the frequency range, that's all. So the answer comes out this time in inverted pole zero form relative to the high frequency gain asymptote. But the values of the corner frequencies are the same. They're just inverted instead of normal. So you see some more flexibility now. You can add elements in series or parallel using the theorem, and you can add any combination of elements as long as it's two-terminal. So already you can begin to see, I think, the power of this theorem. And there's a few more extensions to go yet. So there's the summary of the dual versions. And this picture I've also already summarized. The null double injection calculation is always easier than the single injection one because you use the null condition, which propagates. And you never need to know the relationship between the two inputs that causes the null, because using the null is using the same information. Okay, finally, you get to try one now. Same basic circuit. This time, let's assume the C2 is a complete bypass at all frequencies of interest, so the R is gone. But let's put the spotlight now on the coupling capacitor, which up to now we've taken to be an AC short, which leads to the same mid-band gain of 36 dB that we had before when C1 acts as a short. And so the problem now is we want to account for the coupling capacitor, so we treat it as an extra series element, whose reference value is zero impedance. So the starting point is you break the branch at the place where you want to add the extra element, and you calculate two driving point impedances. First, the ZD. So you apply a second source and you make the first source 0, and now you calculate the ZD. And this is where you take over. Well, let's follow through the argument. Single injection. So you want to know what is the impedance looking in between these two terminals. If you look to the left, you're going to see RS to ground. If you look to the right, you're going to see RB to ground in parallel with the reflected RE. So the total impedance is the sum of what you see looking in the two directions. So the result is RS plus RB parallel the reflected RE. Okay, that's the single injection calculation. Now you do the null double injection calculation. Apply a second source. We store the first source. Double injection. Imagine that the two sources are twiddled to null the output. Propagate the null back to the second source and see what happens to the current that comes from the second source, and that tells you what Zn is. Anyone want to volunteer this one? RS plus RB, that's a possibility. Any agreement or disagreement? RB. This is like the quadratic solution, isn't it? Everyone gets a different answer. No? Maybe they're all wrong so far. Okay, let's follow it through. Propagate the null back to the second source. V2 is 0, therefore 0 current in RL, therefore 0 collector current, therefore 0 base current. But that's not all. Also 0 emitter current. Therefore no drop across RE, therefore no drop across RB. So no current in RB either. So no current in the second source. So regardless of its voltage, 0 current is drawn from it, and the Rn is infinite. Now, you're going to tell me you knew that, but you didn't believe it. Now, in this case, you can get the same answer by an instant shortcut. Do you see what that is? How can you tell immediately that there's 0 current in the second source? Because the two sources are directly in series. The only way you can get a null at the output is to have those two sources cancel each other directly, equal and opposite. That's the adjustment that you need to get the null. So if the two sources cancel directly, there's 0 current everywhere. That's a special case because the two sources happen to be directly in series. So now we have both the RD and the Rn. And the last step is to put the extra element in there, which is a capacitor. And the series form of the theorem says the gain in the presence of the capacitor is the reference gain when it was an AC short, which is AM, multiplied by the series form of the correction factor, in which the Zn is infinite, so the numerator is 1. And in the denominator, Z is 1 over SC1, and ZD is RD, which we calculated. So you get an inverted pole due to the capacitor, and no 0. So the frequency response is the reference gain at infinite frequency, and as you come down, the coupling capacitor starts to open up, gives you an inverted pole and a drop-off of the gain, and the gain goes to 0 at 0 frequency. It doesn't flatten out anywhere because the capacitor goes to infinite reactance at 0 frequency and, of course, disconnects the output from the input. So you have to have 0 gain at 0 frequency. So now you see the calculations are not as complicated or difficult as you thought to begin with. In fact, they're so simple they fooled you. Well, that's a pretty straightforward example, and we'll do this again a few more times as we go along with other things. Now it's time to draw another general conclusion from the application of the theorem that we've seen so far. That conclusion is, if the reference circuit is all resistances, then of course the driving point impedances are also resistances. Rd and Rn instead of Zd and Zn. Second, if the extra element is a pure reactance, such as a capacitor, the theorem correction factor gives you the pole and the zero immediately, because the Z is a reactance and the Zn and Zd are resistances. And you've seen that in most of the examples we've done already. The correction factor gives you the pole and the zero immediately. The only case where it didn't was the one where the extra element was a parallel R and C, in which case the driving point impedances were still resistances because the reference circuit was resistive, but the extra element was an impedance and not a reactance. And so that required one more line of algebra to get the pole zero form. But that simple case, resistive reference circuit, reactive extra element, is what makes the theorem useful in the other range of applications, which, as I mentioned in the introduction, the extra element theorem has two kinds of application. One is where there really is an extra element, and that's what we've dealt with up to now. But the other set of cases is where there's no extra element and you know everything that's there to begin with, but you can use the theorem to break down the analysis into smaller pieces. And that is particularly useful. Remember, you designate one element as extra and you throw it away, solve the simpler circuit, and put the element back using the theorem. So if you take that approach, you have a choice of which element to choose to designate as extra and throw away. And bearing in mind what we just said about that simple case, obviously if you have one reactance in the circuit and everything else is resistive, the element to choose to throw away is the reactance. And then all you solve is a resistive circuit, and you put the reactance back, and the theorem gives you the pole and the zero immediately. So that opens up the other range of applications of the theorem. So there's the generalization I just talked about. And here's the other class of useful applications. Even if you know everything that's there already, designate one element as extra, and the circuit without that element, it becomes the reference circuit. Calculate the property of the reference circuit, and then put the element back in. And this is particularly useful and simple when the designated extra element is a reactance and the reference circuit is purely resistive. Let's look at an application of that. And again, let's use an example we've done already, because it makes it easy to compare the results and see that it comes out right. Here's the lag lead circuit. We already know what the voltage transfer function is. It has a pole and a zero. But let's calculate the result using the extra element. So designate one of the elements as extra and throw it away. And according to the latest principle, the obvious element to choose is the capacitor. Throw it away, and then what's left is a purely resistive network, and it becomes almost ridiculously easy to solve for the reference gain and the two driving point resistances. All you have to do is put the capacitor back into the correction factor, and you've got the answer. Well, this is so easy that I won't even do the example. You try it right away. And you notice that first thing is, even after you've chosen the capacitor as the designated extra element, and you throw it away, you're faced with a choice again. What do you replace it with, an open or a short? Yeah? Why? Well, that's in one way, R2 isn't going to come into it. It isn't going to come into the reference gain, but it is going to come into the driving point resistances. Now what is the consequence of one choice versus the other? If you replace it with an open or with a short, what difference is there in the calculation? If you replace it with an open, the reference circuit is the same as the complete circuit at zero frequency, isn't it? So the reference gain will be the zero frequency gain, and that will come out front in the final answer. On the other hand, if you replace the capacitor with a short, which you could equally well do, then what you're saying is the reference circuit is now the high frequency flat gain. And so the high frequency gain will come out in front as the reference, and the pole and the zero will come out inverted. So you have the choice which way to do it, and the choice is determined by which way you want the answer to come out. Well, since the previous time we did this, we had the zero frequency gain as reference to start with. Let's adopt the same reference this time, which means that when you designate C1 as extra and throw it away, replace it with an open. And that's the only choice that's left, and the rest of it is simply calculating the reference gain and the two driving point resistances. Okay, the first step, dump the element, replace it with an open, and solve for the reference circuit. So here's the V1, R1, RL, and there's the open. So the reference gain is V2 over V1 from this circuit, which is simply the resistive divider formed by RL and R1. Now we calculate the two driving point resistances. So we apply an external source, doesn't matter what the source is, and we calculate RD. I'll immediately write RD now instead of ZD because we know it's going to be a resistance, and it's a single injection calculation, and you make the V1 0. So you look in, and what is the value of RD that you see under those conditions? Right. R2 looking from the bottom end to ground. Looking from the top end to ground, you see R1 parallel RL. Okay. Next calculation. Apply the second source again. This time restore the V1, double injection. Imagine that you adjust those two sources until the V2 is nulled, and under that condition you're going to see Rn looking in between those two terminals. And so this time, what do you get? You get R2. Because from the bottom end to ground, you're going to see R2. And from the top end to ground, top end is already ground because of the null. Remember, the null means there's no current in RL because there's no voltage across it. So the top line is the same potential as the bottom line, namely ground. So between the second source and ground, the only impedance that remains is the R2. Now, if you have a little difficulty understanding the interpretation of this,
I do a little bit because how current comes through R2.
not true. No. There's zero current in RL and zero current here, but a non-zero current around this loop. In fact, the way you get the null is by adjusting these two sources, which are in series around that loop, such that the current that is drawn says that whatever voltage V1 you've stepped up to this point, you step back down to zero at that point. That's what gives you the null. And that same current has to flow through the second source and is going to cause a voltage drop across R2. But in order to get the null, the voltage that you've stepped down through the second source has to be the same as the voltage you step up across R2. So there's a non-zero current around that loop. That's why the impedance seen by the second source is R2, because you got zero voltage across that series combination. The current through R2 is the current through the second source, and they have equal and opposite voltages across them. That's why the impedance seen is R2. Okay, that's almost the answer now. All that's left is to put the capacitor back in and use the theorem. So the theorem says V2 over V1 is the reference gain, RL over R1 plus RL, multiplied by the correction factor for a parallel element, parallel because the reference value was infinite. So it's 1 plus, in the numerator, Rn over Z. And Z is 1 over SC1, so it's SC1 Rn, which is R2. And in the denominator, it's 1 plus 1 over Z, which is SC1 RD, which is R2 plus R1 parallel RL. And that, in one line, is the factored pole zero form for the voltage transfer function of the lag lead network. If you'd like a little more practice in doing this, do the same problem using the reference value of a short circuit instead of an open, and see that you get the corresponding answer with the inverted pole and zero. Okay, so what we've seen at this point is one example now of the use of the theorem to break down the calculation of a known system into simpler pieces by throwing away an element and then putting it back again. And that's a whole different class of applications for the theorem. And as I mentioned in the introduction, there's no guarantee that the calculation will be any simpler than doing it the conventional way. But it's certainly worth considering or even trying. Because again, all the help you can get is worthwhile. So I think this is a good point to stop now, because you've had a new concept to think about and it needs to settle in a little bit. And you have to fit together in your mind all the loose ends to see why things work out the way they do. And you have to go through that process before you believe what you understand. Okay, the next thing we're going to go on to is some further extensions of the extra element theorem. And this is towards a generalization of what we mean by transfer functions. The gain is only one kind of transfer function. And I've written down here 2 or 3 other ones. For example, when you're designing, say, an audio amplifier, the signal input voltage, of course, is the principal independent input signal. And normally you're interested in calculating the gain, which is the signal that comes out of the amplifier. That's your principal specification. But the input signal does something else as well. It also determines the amount of AC current which is drawn out of the power supply for your amplifier. That requires a subsidiary specification, because when you come to design the power supply, or maybe someone else is designing it, you have to provide an interface specification that says your amplifier is going to draw so much AC current out of the power supply, and which therefore has to be capable of delivering it. So another transfer function which is of interest for your audio amplifier is how much current is drawn from the power supply as a function of the signal input voltage. Now this is a dependent current over an independent voltage, and so this is a transfer function which has the nature of a transadmittance, current over voltage. That's another kind of transfer function. A second kind, listed under here, is that the power supply itself is not going to be perfect. It's going to have some rectified ripple on it, probably off the line, maybe 120 hertz or so, may even be a volt or two. And you have another specification on your amplifier that says that power supply ripple in the amplifier output has to be less than some specified value. So there is another transfer function that says, considering the power supply ripple voltage as another independent input, the transfer function that says how much output voltage ripple you're going to get resulting from that is another transfer function that has to meet a specification. That's a voltage over a voltage again, so in a sense it's a voltage gain. Exactly the same sort of transfer function also applies to a regulated power supply itself. That's actually an amplifier as well. And it takes an unregulated rectified line, maybe with a lot of ripple on it, and there is also a specification on the power supply that says its regulated output voltage has to have less than so much ripple in it. So that's another voltage transfer function, which is often called audio susceptibility. That's an important specification of a power supply. These are just a couple of examples to illustrate that the only common thing about all these transfer functions is that the denominator is the independent input and the numerator is some corresponding dependent output. And that's simply a generalized definition of what a transfer function is. And the reason I'm generalizing it at this point is the extra element theorem can be applied to any transfer function, which is not surprising, because as you saw when we developed the extra element theorem, it was completely general, even though I kept referring to specific things like voltage gains as examples. But the diagrams and the algebra was completely general. You don't have to say what the transfer function is. So it applies to any transfer function. So when it comes time to apply the extra element theorem, you've calculated several transfer functions of interest for your system. So I mentioned already, input and output impedances are also transfer functions, as well as audio susceptibility, line ripple feed through, and things like that. So there may be a whole lot of transfer functions of interest to your design. And so partway along your accuracy versus simplicity trade-off, you've made a preliminary calculation of several or all of those transfer functions. And then when you get to the bench and you've made measurements and you find discrepancies and you decide you need to add an extra element somewhere, then you have to correct all of those transfer functions, not just one of them, because the extra element is going to affect several of them, maybe all of them. But the theorem applies to all of them also. So you don't have to go back to square one and calculate every single one of them over again. So if it's an advantage to use the theorem for one transfer function, it's certainly an advantage to use it for the other ones as well. Okay, that's simply widens the spectrum of occasions where the extra element theorem might be useful. Now I want to illustrate applying it to a self-impedance. For example, the input impedance of the same common emitter amplifier that we've had before. Obviously there's no need to show a separate example of applying it to a transfer impedance, because that's obviously the same as a voltage gain. But let's do it for a self-impedance, just to emphasize the fact that impedances are transfer functions as well. Okay, let's calculate the input impedance of the common emitter amplifier, and suppose that we've started by calculating the input resistance of this model that doesn't have any reactances in it. So the input impedance is V1 over I1, where V1 is the voltage of the input, I1 is the current of the input. Obviously, by inspection, the input resistance is RS plus RB in parallel with the reflected RE plus R. The important thing for present purposes about this is that the I1 is the denominator quantity in the transfer function of interest. Therefore, I1 is the independent source. So I should really draw a current source out here, not a voltage source. Haven't drawn either one, but it's the quantity in the denominator that determines what the independent source is. And so for the purpose of calculating input impedance, you're really assuming that you're driving the input with a current and you're observing the resulting voltage. The voltage is the dependent quantity, the current is the independent quantity. That's important because the next step is, if we want to put an extra element into the model, such as this bypass capacitor that we had before, then we have to calculate two driving point impedances, one of which has the input 0 and the other of which has the output null. And that's why you have to be very careful to identify what the input and output are. So I'm going to do this example and also shortcut the writing a little bit, because now we've done enough examples of the extra element theorem that we don't have to redraw the circuit every time for these different conditions. So we can do more of it mentally now. So here's the basic reference circuit. The objective is to put a capacitor across those two terminals, so I've just drawn the capacitor off to the side. That's just a reminder that ultimately that's what's going to be connected. But in order to do that, we have to calculate two driving point impedances. So I've simply represented that as the ZDP looking in at the terminals where the capacitor is going to go. Okay, we have two calculations to make. The first one is we apply a second independent source across these two terminals, and I'm not going to bother drawing that this time either. I've done that enough times using Thevenin's, Norton's, or an unspecified source. Every time I've been saying it doesn't matter what the source is. So now I'm not even going to draw it at all. You just imagine that it's there. So there's a source driving into those two terminals. And the first driving point impedance is ZD, or RD in this case, because everything is resistive. And it's a single injection calculation in which the original input of the transfer function is 0. So this is when you have to be careful as to what the input is. The input is I1, because that's the denominator of the transfer function that the theorem is being applied to. So we have to calculate the impedance looking in at these two terminals when I1 is 0. And the answer is, when you look in, you're going to see R in parallel with RE plus the reflected RB. Only RB. The RS isn't going to come into it because RS is dangling. The other end is open when I1 is 0. So the condition for ZD is I1 is 0, which means an open input, and the answer is R parallel RE plus the reflected RB. So that's the first driving point impedance. The second one, again, I'm not bothering to redraw the picture. We again imagine the second source applied across these two terminals, and we're going to calculate Zn now under null double injection conditions, which means the original input is restored. The original input is I1. So there's an I1 that we imagine being put into the input terminal again. And we're going to adjust those two inputs in order to null the output. What is the output? The output is the quantity in the numerator of the transfer function of interest, which is V1. So you can visualize a voltmeter hung over the input across the current source I1, and we're adjusting the I1 and the other independent source until that voltmeter hung across the current source out here goes to 0. And having established that condition, we ask, what is the resistance looking in? Which is R parallel RE plus the reflected base resistance, which consists of RB and RS in parallel. Because if V1 is nulled, it puts the RS back in parallel with the RB. So that's the answer for the Rn. Now, this is a little tricky, isn't it? Because you've got to remember there's a current source out here, and you're adjusting two sources until the voltage across that current source nulls. But when you're looking in from the second source and asking what is the impedance, it thinks that the RS is back in parallel with the RB, because the voltage at the right-hand end of RS is the same as the voltage at the top of RB, and the voltage at the left of RS is the same as the voltage at the bottom of RB, namely 0. So as far as any currents coming in from the second source are concerned, which is how you calculate the input resistance, it just looks as though RS is back in parallel with the RB. So this is the answer for the Rn. So the important point about this example is proper identification of what is the input signal and what is the output signal for the transfer function, so that you can correctly impose the necessary conditions on the calculation of the two driving point impedances. I want to make sure that sinks in for a little bit, because immediately I'm going to make a modification of that. Okay, the modification is that in the special case where the transfer function that you're correcting with the theorem is a self-impedance, which is this case, in that case, the null double injection calculation gives an answer that can equally well be calculated by simply saying that you look in from the second source with the input shorted, forgetting about the argument to do with the adjustment of the null. Because we've seen that the detailed answer using the null is that RS is in parallel with RB. And you would get the same answer if you just shorted the input. And we've already seen in the previous picture that you get the answer for ZD if you open the input. So that's a shortcut. When you're calculating the correction factor and the two driving point impedances for a self-impedance, you calculate the ZD, single injection, and you open the input, and you calculate Zn, also single injection, by shorting the input. And you don't have to invoke the null double injection condition. So that's a shortcut, because it's very easy to say those words. Let me do it again. To calculate ZD, you open the input, single injection. To calculate Zn, you short the input, single injection. However, I again got to emphasize that the shortcut only works when the transfer function you're correcting is a self-impedance, because that's the only case where the output, V1, is right across the input. If the output is somewhere else, this doesn't work. Okay, let's practice that for a moment. The lag lead network again. Of course, we can use the extra element theorem to work out any function we like by designating one element as extra, throwing it away, using the theorem to put it back in. So suppose we want to calculate the input impedance of the lag lead network. Using the extra element theorem, designate the capacitor as the extra element, throw it out, calculate the input resistance of the reference network, and then find the correction factor. So this is an example where the function to be corrected is a self-impedance. Okay, so there's the reference circuit. And I've again made the choice that when we take the capacitor out, I'm going to replace it by an open circuit. Remember, we have that choice, but by making an open circuit as the reference, then we're again choosing the zero frequency value of the input resistance as the reference. So the reference input impedance is V1 over I1 with the capacitor open, which is just R1 plus RL. Now we have to calculate the two driving point resistances at the position where the extra element is going to go, which is across this pair of terminals here. So we visualize the second source, which I'm not drawing, and we calculate ZD, or RD in this case, under conditions of open input. And because the transfer function is an input impedance, the input signal is I1. So when I1 is 0, R1 is dangling, doesn't do anything. and the driving point resistance is simply the resistance looking around that loop, which is R2 plus RL. So that's the first calculation. And the second one, using the shortcut, is you calculate Rn, single injection, with the input shorted. So that is R2 plus R1 is now put in parallel with RL. So now you have the complete result. The input impedance after you restore the capacitor is the reference value when the capacitor was open, which is R1 plus RL, multiplied by the theorem correction factor for an extra parallel element. So the numerator is 1 plus Rn over Z, and 1 over Z is SC1. So the numerator is 1 plus SC1 Rn, which is the quantity we just have here, and the denominator is 1 plus SC1 RD, and that's the result. Again, constructed term by term in factored low entropy pole zero form. So the purpose of that example is to illustrate that using the extra element theorem to find a correction factor for a self-impedance allows you to use that shortcut. Here's an example for you to work on, the same network, but calculate the output impedance. Using the extra element theorem to throw away the capacitor and then put it back using the theorem correction factor. Output impedance is also a self-impedance. So you can use the same shortcut. Okay, I'll give you a few minutes to work on that, and then I'll go through the solution right away. Start with the reference circuit again, R1. Take the capacitor out and replace it with a short circuit. And the first thing to do is to identify correctly input and output. The function we're correcting is output impedance. So we're going to drive the output with a current. So I'll call it I.O. And we're going to develop a voltage across it, which is VO. And the original input is going to be a short, because the original input for the network was a voltage, but when you calculate output impedance, you're going to drive the output. So the input remains shorted at all times. Okay, so this is now the reference circuit because the extra element has been thrown away. So the output in resistance is, say, ZO with Z infinite is VO over IO, which is R1 parallel RL from that model. So that's the reference circuit and the reference value of the output resistance. Now we have to calculate two driving point resistances. So first we look in where the element is going to go, and we want to calculate RD. So RD is single injection, calculated as the resistance looking in, which is R2 to ground in this direction, and in the other direction R1 parallel RL, because the input is going to be 0. And the correct identification of the input is IO, because that's the quantity in the denominator of the transfer function. So if IO is 0, that current generator is gone, and so you're going to get R1 plus RL for the RD. Second calculation, apply the independent source and find Rn under conditions that the output is nulled, which is equivalent to shorting the input. The input is the IO. When you short it, the VO is 0. So when you look in now for the Rn, you're going to get only R2, because you've got a short across the rest of it now. So that's the result. And that's all you have to do. The rest of it is plugging into the theorem, now that you know the RD and the Rn and the reference value, and that's straightforward. So needn't pursue it any further than that. Now, of course, we're still going through this fairly quickly, and I'm sure you can't fully absorb each step as we go through it. But what I'm trying to indicate is that there is a unique logical process to follow for each of these steps, for each application. And it's simply a matter of practicing it in order to make sure you've identified properly what's input, what's output, what the conditions are for the calculation. So at this point, I think if you just take down these steps, and it's going to take a little longer time later to go over them and see that you could follow the same steps yourself. We're going to get some more practice as we go ahead, because as we talk about other problems, we're going to be using these techniques as we go along in order to get the answers. So you'll see how the whole procedure condenses down to a pretty short process when you really apply these things. In fact, that's the next thing we're going to do. So far, with the extra element theorem, we've applied it to some very simple exercises which we could have worked out by conventional methods just as easily. That's always a good way to introduce a new technique. Very simple problems whose answers you know already. But this is all in preparation for dealing with more complicated problems whose answer we don't know, and that's the purpose of working out the analysis. Now you see where these shortcut techniques really come in to be useful, and that's the next thing we're going to do with the extra element theorem. So where we are right now is we've done another extension of the extra element theorem, which is just a reminder, basically, that it can be applied to any transfer function. It's simply a matter of identifying properly what is the independent input and what is the dependent output for the transfer function that you wish to correct by using the theorem. And there is a special case of that when the transfer function is a self-impedance, in which you can shortcut the conditions for the calculation of the two driving point impedances, ZD basically is a single injection calculation when the input is 0, which is, in the case of a self-impedance, the input is a current, and so the equivalent condition is you calculate ZD when the input is open. That's the same thing as 0 current. And the shortcut for the calculation of Zn is that the Zn is calculated under null double injection conditions when the output is nulled, but when the transfer function is a self-impedance, the output is the voltage which is right across the input current, and therefore the output nulled condition is equivalent to shorting the input. So in that special case of a self-impedance, you don't need to invoke the null double injection condition. You calculate Zn as though it were a single injection calculation with the input shorted. And we did an example of that. And the next thing to go on to now is the application of the Extraelement theorem to achieve an answer that we're interested in for itself. That is, we've just been doing little examples of use of the theorem on problems that we really don't need it. But now we're going to do something a little more complicated, where the Extraelement theorem is simply going to become a convenient tool now in order to get the answer we're looking for. The context of this now is, once again, the basic common emitter amplifier stage, the vehicle we're using for all of these examples. I've gone back to showing the full DC and AC circuit here now, with the bias arrangements, the transistor, the coupling capacitor, the bypass capacitor. And we started out by talking about the mid-band gain of this stage, and then we put in the C2, we put in the C1, using the Extraelement theorem as a convenient way to put those in as extra elements after we calculated the gain at mid-band, which is the AM of 36 dB. The next thing we're going to do is look into the high-frequency response of this amplifier. What I've shown here is the typical sort of measurement that you get after taking the individual data points, maybe, and then doing the eyeball least squares fit of the asymptotes, and that's what leads you to discover the presence of a pole at some relatively high frequency. And according to the measurement that I've made on this particular test circuit, the value of that corner frequency came out to be around 47 kilohertz. So the question is, where does that come from? Because in the model that we've used so far, we don't have any high frequency effects. So according to the model we've analyzed, this gain ought to have been flat up to infinite frequency, but of course in practice it isn't. So now we need to explain where the corner comes from. So we're now, in a sense, in the iteration part of that loop in the design process, where we have to go back and modify the model and see if we can explain the observed pole. So the first thing that comes to mind is that maybe the collector base internal capacitance of the transistor is responsible for the pole. This is a typical small signal amplifying transistor whose collector base capacitance is normally in the range of 5 to 10 picofarads. So at a very rough first order sort of guess, you might think that this would cause the pole because the output collector current of the transistor, which is supposed to go into the RL in order to provide the output voltage, is partially being diverted through the CT. So less of it goes into the RL, therefore the gain starts to drop off at higher frequencies. And if you make a guess that the corner would occur where the reactance of CT is equal to RL, which is the way you normally identify a corner, the corner of 5 picofarads and 10K is about 3.2 megahertz. Obviously, that is not the explanation for a 47 kilohertz corner. The discrepancy is much too large. So rather than dropping the idea and looking for some other cause, suppose you think a little more carefully about whether the CT really is behaving like that. Because the 3.2 megahertz is the corner that you would get if the CT were directly in parallel with the RL. But it isn't. Only one end is connected to the RL. The other end does not go to AC ground, as RL does. The other end goes back to the input of the transistor, which means the current that gets diverted from the output through the CT doesn't go to ground. It goes back into the input and it gets re-amplified. So possibly the effect of the CT is magnified over and above what it would be if it were directly in parallel with the RL. Now, of course, this is not news to you, because you know very well what this effect is, and it's known as the Miller effect, and because Miller is the one who identified this back in the vacuum tube days. The vacuum tube has the same property. It has an internal capacitance between its output and its input. And Miller discussed that, and that's why his name is applied to this principle, and it's exactly the same principle that applies in transistors. So really what we're leading into now is a discussion of the Miller effect. So maybe we shouldn't be so quick then to drop the idea that the CT is the explanation of the 47 kilohertz corner. So let's follow up on that now and get the quantitative result and see whether in fact we do get the multiplier effect. Well, this is now an obvious setup for the extra element theorem again, because the CT is one more element we want to put into the model after we've already calculated the mid-band gain, which we thought initially was going to go up to much higher frequencies. So all we have to do is establish the usual conditions for the extra element theorem, which is we start with the reference model without the CT. This is the one we've already solved for the AM of 36 dB. It's the same model we've talked about several times. But I've simplified it a bit now before we start the calculation, and this gives me a chance to emphasize again the importance of pausing a moment before you jump into the analysis of any problem, which is don't put more in the model than you're going to need to calculate the particular answer that you're looking for. Now, it sounds trivial and obvious to say that, but in practice, it's remarkable how many times people don't think about that point and they put too much stuff in. And that just gets in the way. Makes it more difficult to get an answer, maybe even impossible. And even if you do get an answer, it's harder to interpret it, harder to see what direction the result is going in. So it's always a good thing before you jump into writing equations to make sure you have just enough and not too much information in the model. So what I've done is simplify the mid-band model that we're starting with, in the sense that I've already absorbed the RS and the RB into the Thevenin equivalent. That's the first thing we've been doing all the time anyway when we set out to do calculations on this model. But now all I'm going to be concerned with is calculating two driving point resistances. So all I need to have in the model is enough to give me the right answers for those two driving point resistances. So I've already reduced the model by incorporating the Thevenin equivalent. And just to emphasize again how little you really need, I didn't even bother to write what the coefficient is for the Thevenin source. It's easy enough to do, of course, but I purposely left it out to illustrate the fact that we're not going to need to know what that coefficient is, because when we calculate RD, we're going to make the input 0, and when we're going to calculate Rn, the input is going to be restored, but it's going to be adjusted to null the output, and we know we don't need to know what the input is. So in neither case do we need to know the input. So I didn't write it in. Okay, let's set out to calculate the ZD, or in this case the RD, because the reference circuit is resistive, so we know we're going to get a resistive value of the driving point impedance. Okay, the condition is we apply a test signal across the two terminals where the extra element is going to be placed, and we make the input 0, and we calculate under single injection conditions what the driving point resistance is. Now, this is the first time in these examples where we've come across a calculation for the RD which we couldn't do by inspection, just by looking at it. At least I can't do it by inspection. Maybe you can. If someone can, I'd certainly like to know about it. So I can't tell just by looking at that model what the answer is in the same way that we have done in the previous examples. This means we actually have to back up a little bit and do a real calculation. So what is it we're trying to find? I've identified the current I which is being driven into these two terminals, and the V is the resulting voltage. And the answer we're looking for is the green V divided by the green I under the conditions of 0 V1. I've drawn the independent source as an ideal current generator because, once again, it can be anything you like. Why not make it the easiest thing to do the calculation? So since the denominator is the independent input, I chose an independent current source to provide the test signal. So all I have to do is do as little analysis as possible in order to find V as a function of I. So then I can divide the I into it, and what's left behind is the answer I want. Okay, now I'm about to show you what I believe to be the second shortest method for doing this calculation. Well, why am I not showing you what I think is the shortest method? Well, two reasons. One is, by showing you what I think is the second shortest method first, I can show you another trick of circuit analysis which is useful in other circumstances. The other reason I'm not showing you the shortest method first is that I need to make one more extension of the extra element theorem in order to do that. And I'm going to do that next. So that way we get to see both methods. So what is the second shortest method? And incidentally, there's a whole lot of methods that you could use, and I've tried quite a few of them. And so I've got it down to now what I think is the second shortest method. Okay, one reason why the result that we're looking for is not obvious by inspection is that this independent current source is floating. Neither end of it is grounded. So the trick that I want to show you, which can be used elsewhere, is how do you transform a floating current source into a grounded source, which then makes things easier. So here's how you do it. First thing you do is replace this current generator by two current generators in series having the same value. So I labeled both of these generators I. Now, nothing is any different in the overall circuit, because as far as the circuit's concerned, a current I is being pumped into the base node, and the same current I is being sucked out of the collector node, and it just goes from one current generator to the other. Nothing else happens. So nothing is any different in this model. But we have now developed, at the connection between the two current generators, we have a new node whose voltage is arbitrary. Because by definition, the current generators are going to pump the same current regardless of the voltage across them. So I can give the voltage at this node any value I like. And as usual, the simplest value to choose is 0. 0 being ground in this case. So if I connect this node to ground, AC ground, still nothing is any different anyway. there's no current in this path connecting the node to the two grounds, because the total current I out of this generator goes into the next one. But I can make a little change now. I can separate that connection into two different connections. One of them connected to the AC ground at the bottom, the other connected to AC ground at the top, and still nothing is any different. Because remember, there's an implied AC ground connection from the supply to the bottom anyway. So the circuit still doesn't know anything different happened. But now, you see, this current generator is effectively in parallel between base and ground. This current generator is effectively in parallel with RL. So without changing the topology at all, I can draw them that way. So here are the two generators placed directly across the relevant nodes. Still nothing is any different. By now you've forgotten what we were setting out to do, which is to calculate the green V as a function of the green I, and we have now replaced the floating source I by two grounded source I. But it's the same I. Okay, now we could continue to do the algebra on the circuit diagram. We could make some further reductions. But remember, we have a lot of choices, a lot of directions to go in when we're trying to achieve a certain answer. So arbitrarily, I'm going to leave the diagram in this form now and then continue with the algebra, which you can see at a glance is still fairly lengthy. So let's just walk through the steps just to describe what the process is. We're trying to solve for the green V divided by the green I. The green V is equal to the sum of VBE and V2. I should say that the algebraic sum of all three of them is 0 because we got AC ground at the top and the bottom. Okay, so I can separate the RD into the sum of two terms. I can find the VBE as a function of I because I have a current source I developing a voltage right across it determined by the resistance RG in parallel with the reflected RE. This is just a Norton source here, basically. The impedance across the source is RG in parallel with the reflected RE. So this is the relation between VBE and I. That takes care of the first term in the result I'm looking for. Now I also need to know what is V2 as a function of I. V2 is the voltage across RL, which is driven by two current sources, one of which is I, and the other is the collector generator beta IE or alpha IE. Same thing. But the IE I can find in terms of the VBE. IE is VBE over RE. So I've assembled now all the pieces I need. Here's V2 as a function of I and VBE, and here's VBE as a function of I. So all I have to do is plug those into this expression and manipulate the algebra, keeping the entropy as low as possible as I go along. So I won't go through each of those individual steps. You can see it's fairly lengthy. It takes a fair amount of algebraic control to keep that in low entropy form to arrive eventually at this answer at the bottom. And the first thing you notice about the answer is it's fairly complicated, which means that whatever method you can think of to arrive at this answer is probably going to be fairly lengthy. Since the answer is complicated, then probably it's going to take a fair amount of work to get it, however you do it. Which is why the answer isn't obvious. Because I think when you look at what the answer is, it's pretty clear you wouldn't be able to come up with that just by looking at the original diagram. Okay, so the important thing is, what does the answer tell us? Well, when you put numbers in, you see that this coefficient in front is a fairly large number, and it multiplies the RL. And look at how these numbers are derived. Again, the importance of retaining the low entropy format and plugging in the numbers in an intermediate step so you can see which ones are important. The numerator is RG parallel the reflected RE, and they happen to be numerically almost equal in this case, which means the parallel combination is about half either one of them. When you look at the denominator, it's a triple parallel combination of RG, RE, and RL, and it's dominated by the small one, which is the RE of 36 ohms. The other two hardly make any difference. So the net result is that the numerical value is about 2.2K in the 2.4K in the numerator divided by 36 ohms. That's why the answer is a large number. Since RL is 10K, the RD is 620K. Well, we'll come back to the interpretation of that after we finish the calculation, but all I will mention about this one is that I chose this method to illustrate the trick of replacing a floating current generated by two separate grounded ones, which you can use in other places as well. Well, that's the RD. Now we still need another driving point resistance, which is the Rn. Okay, now back to the model with the independent source outside. This time the original input is restored, but we still don't need to know what its value is because we're going to adjust the two sources to null the output, and using the null is all we need to do. So we go through the same steps. We propagate the null back to the second source in order to determine how much current goes through it. So before I do that, notice just by looking at this line underneath, it doesn't take much to do that. Now, I've been suggesting all the way along with the Extraelement theorem that the calculation of the Zn is always much easier than the calculation of Zd. Now, in the examples we've had up to now, it hasn't made much difference because they've been very simple examples. This is a more complicated one, and notice that what happens is it's the Zd that gets worse. The Zn stays simple, in spite of the fact that it's conceptually the new thing, which is causing you a little trouble still, but it emphasizes the fact that the Zn always stays a simple calculation, even though Zd gets to be pretty messy. Well, let's see why it is so easy to get this answer. You use the null, you propagate it back. So the first step of the argument is, if V2 is 0, there is 0 current in RL. Now previously that meant 0 collector current also, but it doesn't mean that this time, because there's another connection to this point. What it does say is that the collector current is equal to the current to the second source, because there's no current in RL because of the null. So the current in the second source is equal to beta IB, but that current I've already defined as minus I. So in the denominator, V over I that I'm trying to calculate, the denominator I I've replaced by minus beta IB. The second step is I want to know what the V is. The green V equals the red V. Again, because there is a null across the output. So this is AC ground at the output. So if I step up by a green V from AC ground to the base, then I have to step down by the red V the same amount to get back to AC ground again. So the green V equals the red V. But the red V is the drop across RE, which is the emitter current 1 plus beta IB times RE. So I substitute that for the V in the numerator. The IB cancels. 1 plus beta over beta is 1 over alpha, and the answer is minus RE over alpha, or minus 36 ohms. So that's a very short, simple process, certainly compared to the ZD calculation. Okay, any difficulties about that? Because we've almost finished with the theorem now. We're going on now to see what the answer is telling us about the properties of the amplifier. Okay, let's assemble the result. We now put the CT in. That's the extra element. And the result is the gain in the presence of the CT is the reference gain AM that we started with, multiplied by the correction factor for an extra element in parallel. So it's the first version of the theorem, 1 plus Zn over Z in the numerator. The 1 over Z is SCT, and the Zn is Rn. And in the denominator, 1 plus SCT RD. So once again, the correction factor gives you the 0 in the pole immediately, because this is the special case where the reference circuit is all resistive and the extra element is a pure reactance. Okay, now we can see what the circuit does, which is what we're trying to find out. And you see there's a couple of peculiarities. The first is that the Rn is negative. And that means that the 0 is a right half plane 0. The one that has a phase lag instead of a phase lead. Now, this is why I wanted to do the solution of that example earlier on before we got to this. This is a case where a right half plane 0 shows up in an actual circuit. And you see, it's the same structure that I gave as the example earlier on, which could lead to a right half plane 0. It's the parallel combination of two signal paths which change places, going from 0 to infinite frequency. This is exactly that situation. Because without the capacitor, the reference circuit is a high gain inverting amplifier. But it has a parallel path through the CT, which is a non-inverting path of low gain. So it's exactly that block diagram setup we had earlier on. And so at low frequencies, the high gain inverting path through the transistor dominates, but the capacitor causes a low frequency pole and it loses its gain, which we haven't talked about yet. It's part of the answer. But then at very high frequencies, the CT effectively becomes a short circuit. So it dominates the transmission from the V1 to V2, because the output is basically strapped right back to the input at infinite frequency with a low gain. In fact, a gain less than 1. So it satisfies exactly the conditions where you have a high gain phase inversion with a flat gain at low frequencies, which ends up being a much lower flat gain at high frequencies, which has to be 180 degrees different. So that's why you get a right half plane 0. Now, this is one of your basic building blocks in most of your products, I guess. So you use this all the time. Why haven't you noticed the right half plane 0? Well, this is why you haven't noticed it. It's 880 megahertz. You haven't noticed it because lots of other things have fallen apart before you get to this kind of frequency. In other words, the model is no longer adequate to explain what really goes on at frequencies like that, and you don't care anyway, mostly. So, because of the numbers, you may not have noticed the fact that the right half plane zero exists. But it's not too hard to visualize some circumstances where the numbers may be radically different. For example, suppose the CT were not 5 picofarads, but 5 nanofarads. Not because the transistor would be that lousy, but you often purposely put a capacitor in that position, externally. Okay, so if the capacitor is 1,000 times bigger, this is now 880 kilohertz. Now it's down to a range where it may get in the way of some things you're looking at. That's one reason. Another reason may be, suppose you have an unbypassed emitter resistor down here, like the 2.2K we've had in the previous examples. It adds directly to the RE, and we already know the Rn is minus Re, and if it has an R in series with it as well, which is 3 orders of magnitude larger, that also brings this frequency down by 3 orders of magnitude. And suppose you have both of those things at the same time, bigger capacitor and bigger resistor, then you may be down into the low kilohertz region. So one thing to think about now is right half plane zero in this stage may not be of any concern, but if you have widely different numbers, it may come into having some effect, and it may be the cause of some difficulties you might have had and not really known why. Especially when you remember that the phase contribution of the right half plane zero is going to come in even an order of magnitude below where the corner itself is. And then maybe you're going to put feedback around one or more of these stages, where the phase angle of your loop gain becomes very important in determining stability. So you see there's all sorts of multipliers that may cause this effect to be more significant. Well, enough about the right half plane zero for the moment. We're still going to come back to it later on, though. But for the moment, let's dispose of it, because at least with these numbers, it isn't going to be of any concern. Now let's look at the pole. The pole is the CT with the RD. And the RD, remember, is a large multiple of the RL. So we need to look now into where that multiple comes from. Okay, this is disposing of the right half plane zero, and this is looking at the pole now. I'll give a symbol to that multiplier. Obviously M is a good symbol because it stands for multiplier and it also stands for Miller, so that makes it very nice. And it's this ratio of parallel quantities. So I rearranged that a little bit to expose the fact that this multiplier is a function of the source resistance, which in a sense is external to the amplifier stage itself. And it's important to recognize that this multiplier does depend on the source resistance that you're driving the circuit from. In fact, you can easily see that it's a bilinear function of that resistance. Because if you multiply out the parallel terms, you end up basically with an RG plus something over an RG plus something else. That's a bilinear function. So it has two extreme values. And those two extremes are, if RG is very large, this ratio tends to 1 plus beta. Because if RG is large, its paralleling effect goes away, the RE cancels, you're left with 1 plus beta. At the other extreme, if RG vanishes, the ratio goes to 1. So the multiplier can have a large range of values. depending on the value of the source resistance. Now the multiplier is inside the RD, so it determines the pole of your amplifier gain, which basically determines its bandwidth. So if you're trying to make a wide bandwidth amplifier, you want to keep the multiplier as low as possible. This tells you you better keep the RG as low as possible also, which you probably know already as well. But this is a very compact summary of all that. In fact, it's even useful to plot a little sketch of the value of the multiplier as a function of RG. And here's the graph of that function. And it's also convenient to use a double log scale, so that the same geometry to do with asymptotes that we already know all about can apply to this case as well. So here I plotted the multiplier on a log scale versus RG, also on a log scale. This exposes the low RG asymptote of 1, the high RG asymptote of 1 plus beta, and in the intermediate range, it's a single slope, 1 for 1 again, or 20 dB for 20 dB, or 20 dB for an order of magnitude, however you want to interpret it. But notice you get another important piece of information out of this. You get corner resistances, just like corner frequencies. And here are the values. The lower corner resistance is Re. The higher one is 1 plus beta Re. What this tells you is, if you consider the Rg as a design parameter that you have some control over, and you want to make a high bandwidth amplifier, then you want to keep the M low, so you want to be near the bottom end of the sketch. So you make the Rg small. What this tells you is you can make it as small as about Re, and there's no further benefit in making it smaller than that. Likewise, at the other extreme, if you're not that concerned about bandwidth and you like to use a high Rg, what it says is by the time you get to an Rg of 1 plus beta Re, the bandwidth is as lousy as it's going to get, and you can make the Rg much larger than that and you won't be any worse off. So you see there's a lot of useful interpretation you can get out of that little sketch. One refinement about it also. These represent asymptotes, of course, and the actual function, M as a function of Rg, of course, has smooth corners, just like the frequency response really does. In frequency response, remember the actual curve is 3 dB away from the asymptote intersection. In this case, the smooth curve is 6 dB away from the asymptote intersection. Why is there a difference? Yeah, I think what I'm hearing is you're saying the variable in this case is resistance, not frequency. In other words, the variable is a real variable, frequency is an imaginary variable, S equals J omega. So when you calculate the magnitude of the frequency response, you take the square root of the sum of the squares, root 1 plus omega, J omega squared. But this is a real function of a real variable. So it's simply 1 over 1 plus 1 at the corner, or 1 over 2, not root 2. So you get a 6 dB corner instead of a 3 dB corner. In fact, the numbers that we had right here, if I can find the earlier picture, here it is. If you look back at this picture, Rg and 1 plus beta Re are 4.6K and 4.3K. And beta is 120. So the value of this asymptote is 120. And the actual value of Rg we have in this example is almost at that corner. Because 1 plus beta Re is 4.3K and the Rg was 4.6. So we're just about at the corner. So the M is 6 dB down below the 1 plus beta, 6 dB or a factor of 2. The beta was 120. Half of that is 60. And M is 62. So that's consistent with what we've already said about this interpretation. So in this example, we happen to be just about right on that corner. So as a high-frequency amplifier, this is a lousy design. Okay, notice on this picture I've made an equivalent circuit modification. I've unhooked the CT from the base and reconnected it to ground, and I can do that as long as I multiply the CT by N, because I have now placed that capacitance directly in parallel with the RL, so that if I compute the bandwidth or the corner frequency by just finding the corner of RL and this capacitance, I'm going to get the right answer for the pole, the omega 4 that we've had in the example. And in fact, that does come out to about 47 kilohertz. Now, I started out by assuming that the CT was 5 picofarads, and 3.2 megahertz divided by 60 would be about 50 kilohertz, and I've actually measured 47. So I can work back, in fact, to find what the CT really was, which was a little bit more than 5 picofarads. Of course, I make this measurement of the frequency response by putting a 10-to-1 scope probe across the output. And the scope probe has 13 picofarads of capacitance. But that isn't going to upset my result, because I have to compare the 13 picofarads not with 5.5, but I have to compare it with 62 times 5.5, which is 340. So the probe loading is essentially negligible. So when I make this substitution, I have to multiply the value of that capacitance by the M in order to get the right answer for the bandwidth. So it's an equivalent circuit in that sense. But it's hazardous to do this. I get the right answer for the bandwidth of the gain, but I wouldn't get the right answer for the input impedance. Because in this model, the input impedance would be resistive, whereas when that capacitor is in its proper place, it isn't resistive. It's complex. So you've got to be a little careful about equivalent circuits. Equivalent circuits give the right answer by definition. That's why you make them. I said that already. But you've got to be careful. What is the answer you're looking for? And an equivalent circuit can give you the right answer for one function, but not for another. So you've got to be a bit careful when you make this transformation related to the Miller effect, by remembering that it only gives you the right answer for the gain of the stage, not for any other properties. Now, you've heard about the Miller effect before, and you usually think of it in terms of this interpretation, where the effective value of the capacitance is multiplied. You may also remember the Miller effect in the sense that the value of the multiplier is usually expressed as 1 plus the voltage gain of the stage. If that's A, then the effective value of the capacitance is 1 plus A times CT. Is that, do you sound familiar? Is that the way you use the Miller effect? You notice I've avoided saying that. And the reason is that by saying the multiplier is 1 plus the voltage gain of the stage, that's correct as far as it goes, but it doesn't go as far as reminding you that the voltage gain A itself is frequency dependent. So when you multiply a capacitance by a frequency dependent gain, it's not a capacitance any longer. It's something else as well. And that is in fact what gives rise to the right half plane zero. But you see, the right half plane zero is not explicit in the usual Miller interpretation of this. It's implicit in the fact that the voltage gain A is frequency dependent, but you tend to forget that. So the standard textbook treatments of Miller effect are a little dangerous. They look nice and simple, but they hide the fact that that voltage gain is frequency dependent, and it has to be accounted for to give you the right answer at high frequencies. Okay, this is, I think, a pretty nice example of a problem which is moderately complicated, and where the extra element theorem was a convenient way to get answers pretty simply, and where the center of interest in the problem is the answer and not the method. But that's what all these methods ultimately are for, of course. Well, to remind you of the context of this, I said I'd showed you what I think is the second shortest method of getting the ZD driving point impedance. So what is left to show you, which is the last thing to talk about, to do with the extra element theorem itself. That's one more thing to do. I kind of lost track of the time. I think we've overshot another break by quite a bit. So why don't we have another rest before we go on to that last step? Well, in this application of the extra element theorem to finding the two driving point impedances to add the collector-based capacitance, I mentioned that the method we've seen so far for calculating the ZD is not really the shortest method. So now that's the last thing to do with the extra element theorem, and requires a little extension of the theorem. There are two forms of the extra element theorem, depending on whether the reference gain that you're starting with corresponds to the element being infinite or the element being zero. They're dual forms. And we found the second version, that for the series element, was obtainable in a couple of lines of algebra from the first one. In fact, this is how we did it. This is the same picture we had earlier on, starting with the element theorem for the parallel element. Then we pulled out Zn over Z from the top, Zd over Z from the bottom, the Z's canceled. And then the emphasis at that time was the interpretation of this entire coefficient in front must be the gain of the system when the extra element is zero. So we ended up with the two dual forms of the theorem, and we went ahead from there. And I pointed out at the time that this was a direct analogy with frequency response. You could either use the zero frequency gain as reference or the infinite frequency gain as reference, and you have either a normal pole and zero or an inverted pole and zero, and this is exactly the same thing except the variable is impedance instead of frequency. Now there was one aspect of that that we weren't concerned with at the time, but we can now use. Namely, the definition of the gain when the extra element is zero is that it's the gain when the element is infinite multiplied by the ratio of the two driving point impedances, which is this, or rewritten in a symmetrical form, this part of it, which is also symmetrical or dual of the frequency response interpretation. The ratio of the two flat gains is equal to the ratio of the corner frequencies that separate them. This is the same thing where the variable is impedance. So the ratio of the gain of the system when the element is zero to the gain when the same element is infinite is the ratio of the two driving point impedances seen by that element. It's sort of a redundancy relationship. Now, the way we've been applying the theorem is we know one of these gains, because that's where we start from with the original circuit. And then we calculated the two driving point impedances in order to determine the correction factor. We found that calculation of the Zn is always easy. Calculation of the Zd may get more difficult in more complicated cases. Now, we have an additional piece of information, the redundancy information, which suggests that we know one of the reference gains, Zn is easy to calculate. Instead of calculating Zd directly, maybe it would be easier to calculate the other reference gain. And then you can find Zd from this ratio relationship, which would be easy to do because it's only products and quotients involved. So even if you have factored pole zero forms for all of these, which is desirable anyway, to calculate Zd from the other three simply involves products and quotients of the poles and zeros, and there's no cross-multiplying and refactoring to do. So it would be an easy process also. So let's check up on that with the example we've just done. How to put the collector-based capacitance of the transistor into the model and determine the frequency response. In that case, the reference gain was the gain when the element Z was infinite. That's the AM that we started with. It was also easy to calculate the Zn. Took only 2 or 3 lines. Very simple. So now, instead of calculating the Zd directly, let's calculate the other reference gain, which means you go back to your reference model and now you simply put a short circuit in place of the extra element. Already you can tell it's going to be easy. Because if you short the collector to the base, the transistor collapses to a point, like a black hole. And all you're left with is a simple resistive divider to calculate the gain, V2 over V1. So here it is. The gain when the Z is 0 is the divider ratio from the Thevenin equivalent that you have to begin with, and then the other divider ratio that comes out of the circuit model, which is this. So then, using the redundancy relationship to find Rd, it's equal to the Rn that we know already, multiplied by the ratio of the midband gain that we started with, divided by the gain when Z is 0 that we've just calculated. And there's the answer, which is a lot shorter than that long derivation with the circuit reduction and then still quite a few lines of algebra to deal with. So we've wiped out all the difficult part of the previous calculation. So this gives you another degree of freedom. when you're applying the theorem, because of that redundancy relationship, you need only 3 out of the 4 quantities, and obviously you want to calculate the 3 easiest ones. And I think from this example you can see that quite often it might be easier to calculate the other reference gain than to calculate the ZD directly.